Hey guys, let's get started. So, so we learned about how to design a test bench in the previous class, right? So, and then, so in this time, so we will learn about the timing property of sequential logic. So actually, so this topic is very important. So it is because, so as I mentioned, the most digital systems include clock signal, so which means that the digital system digital systems include deep flip-flops and combinational logic between deep flip-flops. And then, so actually, so which means that this is so this is kind of the system. It's a system, and then this system receives clock signal. Okay, this clock signal. So it includes the reset, but actually in this time, so we will learn about the timing property of this sequential logic. So this clock signal is very critical. It's very critical for the performance of this digital system. So I believe so you are interested in the performance of CPU or some processing units. Then I believe that you can focus on the clock frequency, right? Okay. So so recently, so many people use mobile devices, but so actually the performance of a mobile devices is usually lower than the performance of our laptop or desktop computers. But for the desktop or laptop computers, usually, so I said usually the performance of computer systems is determined by clock frequency. Okay, so we can simply compare the performance of a CPU using clock frequency, such as this is the CPU A, and then this is the CPU B, and then the clock frequency of the CPU A is 5 gigahertz. And then, clock frequency of CPU B is 3 gigahertz. So, I said usually, so actually the performance of computer systems is determined by many factors. Okay, so which means that we cannot compare the performance of these two systems only using clock frequency. But if the other factors are the same, then we can just compare the performance of this system using clock frequency, right? And then we can say that CPU A has higher clock frequency, so which means the performance of a CPU A can be higher than the performance of CPU B because it has higher clock frequency. Okay, so usually the performance is proportional to the clock frequency. And then what is the frequency? What is the frequency of clock signal? The frequency of clock signal is the inverse of, so F is inverse of clock period, right? So which means that, so we can say that clock period, so the period of this clock signal determines the performance of our digital system. And the clock, the period of this clock signal is determined by delays, the timing properties of deep flip-flops and combinational logic. So that's why I said that this topic. So today's topic is so very important. And then, so I hope you can understand how the clock period actually. So how the clock period is determined in a digital system. Okay, so that's so I believe so now. So I believe I showed this slide many times, right? So actually this slide compares the combinational logic and sequential logic, and then you can just compare that combinational logic is memoryless, right? And then sequential logic has memory, right? So you can just compare the combinational logic and sequential logic based on memory. Okay, so and also I showed this slide before, right? So actually, so we can understand. So we can understand the basic design policy. So basic design approach of our digital system is similar to this figure. Okay, so as I mentioned, so there are many state elements, and that I said that these state elements are actually D flip-flops. Okay, so D flip-flops, and then also this is the D flip-flops. And between two D flip-flops, and then there is combinational logic. Okay, and then we already know that the combinational logic, the output is just determined by input signals, right? So this is the input of combinational logic, and then combinational logic generate output, but after some delay of this circuit. So we also learned about the propagation delay and contamination delay of the combinational logic. So propagation delay is the maximum delay, of the combinational logic, and the contamination delay is the minimum delay of this combinational logic, right? And because this combinational logic has a delay, actually this the delay. So the output of this combinational logic needs to be stabilized. So which means that actually the delay, the maximum delay of this combinational logic needs to be lower than the period, of this clock signal, right? So if you see this figure, so you can find that the input signals of combinational logic is the output of D flip-flops, right? And then when the output of D flip-flop is updated on the rising edge of clock, so which means that this input, the input signals of this combinational logic is initialized, so it's updated on the rising edge of clock. So those input signals start at the rising edge of clock, right? And then after some delay at the t, then output signals are generated from combinational logic. And then, so this is the output signal. And then the output signal from combinational logic is also sampled by on the rising edge of clock, but it's the next clock, right? So the input start at this point for this combination logic, and then output is stabilized at this point. But the output signals need to be stabilized before the rising edge, the next rising edge of clock signal. Okay, so this is very important. Okay, so if the delta t, the delay is longer than the clock period, then actually this deep flip-flop will sample incorrect output. And then if a system generate incorrect result, then no one will use this system, right? So that's why the delay, the timing property is also very critical. It's very critical for the actually the reliability. So I said that if the results are incorrect, then no one will use this system. And then, so this is called the reliability issue, right? So reliability means that, oh, I can believe this system, right? So if this system is reliable, then we can say that, oh, I can believe the output of this system. But if the system is not reliable, then the system may generate incorrect output. Then we can say that, oh, I cannot believe the output of this system, and no one will use this system. Okay, so the timing of the system is critical for the reliability of the system, and actually the timing of the system also determines the clock frequency. So which means that the timing can also determines the performance of a digital system. Okay, so I hope you can understand this, and then let's learn about some timing properties of sequential logic. Okay, as I mentioned, actually, even though we learned about some many different kinds of sequential logic, such as the bi-step logic, latches, and then some flip-flop, but actually, so we frequently use deep flip-flops deep flip-flops in the digital system. Okay, so let's learn about the timing of flip-flops. I also mentioned that so usually we do not use latches. Okay, latches can be used for some special circuit, so specific circuit. Okay. Okay, so let's learn about the timing of flip-flops. So flip-flops sample D at clock edge, right? So this is the flip-flop, and then this clock signal, and then this is D, and then this is Q. So this is the input of flip-flop, and then as we learn the output Q. Output Q is Q becomes transparent to the input only on the rising edge of clock, right? So at this point, so the input signal of D flip-flops need to be stabilized. So stabilized before the rising edge of clock signal. Okay, so you can understand the property of this D flip-flop like the camera. So if the object is moving, and then if we just take the picture using a camera, so actually recently most people take the picture using smartphone. So it's the same actually. So we can just touch the take a picture button, right? So let us assume that we are taking the picture using our camera, but if the object is moving, then we can observe unstable. So it's like not incorrect, but because the object is moving, then we can just observe some blurred and then undesired picture, right? Why? If the target object is still, so it does not move, then we can get clear image using our camera. It is because the camera just take the picture by opening the lens, right? For a short time, right? And then during this short time, if the object is moving, then we can get incorrect or some the blurred image. But if the object is still, so which means stable, then we can get clear image, right? It's the same because actually in the camera, the lens is open during very short time, and then the image is sampled. Okay, so you can understand the deeply block like this. So deeply block samples the input signal, right? Like the camera samples the input images, but deeply block samples input signals, but during very short time. So during this very short time, the deeply block samples the signal, and then if this signal is unstable, then the output. So we can get incorrect or unstable output signal. Understand? So we need to consider the property, the timing property of this deep flip-flop. So try to understand this property like the camera that samples the input images. Okay. So for the input signals of this deep flip-flop, then we can consider the two timing constraint, the two timing characteristics of a deep flip-flop. The first timing constraint is the setup time, and then the second timing constraint is hold time. So setup time means that, so this is the rising edge of deep flip-flop, right? And then I said that the input signal of deep flip-flop needs to be stabilized before the rising edge of clock. So actually, and then theoretically, the rising edge is actually occupies zero time theoretically, right? This is the edge. So it's an edge, but actually in reality, so actually we can observe the clock signal like this. So we can observe the slope of the clock signal. Okay, and because the deep flip-flop is also a real circuit, actually the input signal needs to be stabilized before this T setup time before the rising edge of the clock. So theoretically we can say that input signal needs to be stabilized this rising edge of the clock, but actually, so we need to consider some time, okay, before the rising edge of the clock. So actually, the input signals need to be stabilized setup time before the rising edge of clock. Okay, so we can find. So this is the rising edge, and then before the setup time, then the input needs to be stabilized. Okay, so this time is called the setup time. Also, we can observe another timing constraint called hold time. So hold time means that after this time, hold time, T hold, after the rising edge of the clock, the this input signal of this T flip-flop needs to be maintained. So, which means if the input, okay, if the input signal is changed before this hold time, then the flip-flop may generate the incorrect output or unstable output. So the input needs to be kept, maintained during this hold time. So there are two timing constraints. The setup time is that the input needs to be stabilized. So which means that input signals cannot be changed. So input signals need to be stabilized before the setup time on the rising edge of the clock. Also, the input signal needs to be maintained. So input signal cannot be changed. Input signal needs to be maintained after the hold time on the rising edge of a clock. So we need to consider this T setup or T hold for calculate for analyzing the timing property of D flip-flop. Right. So this is the two main timing constraint of this D flip-flop, and then actually this T setup plus T hold is called the aperture time. Okay, so actually T it's called the TA. So TA is equal to the T setup plus T hold. So what is the aperture? So aperture means it's the terminology of camera, right? So actually, so aperture means that it's the lens is open for a short time, and then this is called the aperture time, right? So actually, so you can just understand that this is the shutter of a camera, and then actually the object, the input signal needs to be stabilized during the aperture time. Okay, so you need to you can understand the timing property, the setup time and hold time like this. Okay, so just based on the rising edge of the clock, and then during the setup time, the input needs to be maintained. Input needs to be stable. Okay, so which means that the input signal needs to be stabilized before the setup time on the rising edge of the clock. Also, the input needs to be stable, okay, during the hold time on the rising edge of the clock, based on the rising edge of the clock. So which means that the input needs to be stable during this hold time. So around this rising edge of the clock, and then during the aperture time, the input of a D flip-flop needs to be stable. So this is the very critical, very important timing constraint. Timing constraint of the D flip-flop. So constraint means that we need to keep some rules restricted by some constraint, right? So which means that when we design the system, we need to keep this rule, this timing rule, and then if this timing rule is violated, then we cannot guarantee the correct behavior of the system. Okay. Okay, so this is the some timing property of input of D flip-flop, and then we can also consider some delay of output port of this D flip-flop. So this is because D flip-flop has also the output signal output port Q, and then this Q is also changed on the rising edge of the clock. And then T flip-flop is also a circuit, the electric circuit, and then T flip-flop also exhibit the delay of output signal. So we can also observe we can also consider the propagation delay and then contamination delay. So like the propagation delay of the combinational logic, the propagation delay of this deep flip-flop is the delay of Q from the rising edge of the clock. Okay, so as you can see, you can find the TPCQ. So which means that the output is actually stabilized after this propagation delay of the output port Q. Okay, so we guarantee that the output of this deep flip-flop is stabilized after TPCQ. Okay, this is the maximum delay. The maximum delay of the output port of deep flip-flop. Okay. Also, we can consider the contamination delay. So this is the minimum delay. Okay, so we learned about the contamination delay of the combinational logic, right? So it's the same. So contamination delay of this deep flip-flop is the minimum delay. Minimum delay of this output port. Okay. So actually, we learned about this propagation delay and then contamination delay in the combinational logic. It's the same. Actually, the meaning is the same. So the propagation delay and then contamination delay explains the timing property of output port, the output signals, right? It's the same. It's the same for this deep flip-flop and combinational logic. But for deep flip-flop, so this is some timing constraint between the clock edge and input signals. So this is the unique feature, so unique timing constraint of deep flip-flops, but actually, so it's a very critical, it's very important. So this timing constraint explains some timing characteristics of deep flip-flop for the input signal. Okay, so you need to understand the setup time and hold time, and then because using the setup time and hold time, we can analyze the timing property of digital systems. Okay, so and then as I mentioned, so this is the dynamic discipline. So we can just restrict some behavior. So okay, you can just restrict some explanation, description of some system. Okay, so during this aperture time, so which means that during the setup time and hold time, the input must be stable. So that's what I explained. Okay, and then also, which means that so as I mentioned, so this is some basic timing model. Okay, so it's some basic design approach of the system. So as you can see, you can find the two flip-flops and then combinational logic. So dynamic discipline means that this combinational logic. So actually from this part, so this is some input. So it's some start point. start point of the this input signal, and then this is the some end point. End point of the this circuit, right? So like the so this is the start point, and then this is the end point, and the timing between the start point and then end point needs to be lower than the clock period. The clock period of this clock signal. So we can find the TC is here. So TC is the clock period, right? And then we can calculate. We can calculate this minimum delay of this circuit and then the maximum delay of this circuit. So it means that it's a TC. So on the rising edge of the clock, then Q1. So Q1 is the output of this D flip-flop, right? So it means from this rising edge of the clock, we can calculate the minimum delay and maximum delay of this Q1, right? Right, because we learned. So we learned about the propagation delay. So this is the maximum delay and contamination delay of the port Q in D flip-flop, right? So which means, oh, for this Q1, we can calculate the minimum delay, and maximum delay for this Q1. Okay, we can also analyze, calculate the minimum delay and maximum delay of this combinational logic. Okay, so as I mentioned, the combinational logic is located between two flip-flops. So based on this minimum and maximum delay of the Q1, and then also the minimum and maximum delay of this combinational logic, we can calculate also the minimum and maximum delay for this D2, right? And this minimum and maximum delay for this T2 needs to be actually, it needs to be lower than the clock period. But also we need to consider the setup time and hold time. Okay, so this is the dynamic discipline. So let's run. Okay. Okay. 그거랑 상관이 없어요. 그러니까 그 테스트 벤치는 그냥 오직 시뮬레이션이고, 여기서는 그냥 하드웨어로 우리가 신테시스 했을 때, 하드웨어로 임플레멘테이션 했을 때 그때의 진짜 딜레이를 지금 다루고 있는 거예요. Okay, it's a good question. So he asked about some delay we learned for the simulate for the test in the test bench, but you need to remember that test bench is just simulation. It's fake. Okay, so actually for the simulation, so we just use the delay, but this delay is just avoid some time. So it's like the exact timing of the rising edge. So we just add some delay after the rising edge for the input or output signals. But in this time, I am explaining about some real timing. So our design can be translated into logic gate, and then logic gates are actually implemented using electric circuit, so real circuit. So if the real circuits are implemented, then we can observe delays, okay, real time. So I am explaining about this real delay, the real delay of circuit. Okay. Okay, so let's learn about the setup time constraint. Okay. So firstly, so we need to consider the minimum and maximum delay for this one, and then by doing this, we need to make the circuit that keep the setup time constraint. Okay, so which means that our design needs to meet the this setup time constraint. So then what's the setup time constraint? Then what's the setup time? So when I explained about the setup time, I said that input of D flip-flops needs to be stabilized. The setup time before rising edge of the clock. Right. So this is our model. So Q1 is the input of the combinational logic. Then this is combinational logic. Then D2 is the output of combinational logic. And then also D2 is the input of flip-flop R2. Right. Q1 is the output of R1, and then this output becomes the combinational logic. So I said on the rising edge of the clock, then this input. So if we just focus on the R2, then on the rising edge of this R2, D2 needs to be stabilized. This setup, the setup time before the rising edge of clock. So this is the setup time constraint. Then how can we analyze? How can we analyze this setup time? Analyze the timing for considering setup time constraint. So I said, oh, this output D2 needs to be stabilized. Okay. Then how the timing of D2 is determined? So do we need to consider the minimum delay or maximum delay for this case? This D2 needs to be stabilized before a certain time. Okay, so which means that we need to arrive to this point before a certain time, right? Then do we need to consider the maximum delay, or do we need to consider the minimum delay? We need to arrive before this time. We need to consider maximum delay, right? 맞잖아요. 우리가 언제까지 도착해야 된다. We need to arrive at certain time, and we can start a certain we can start, but for this situation, we need to consider the maximum delay. Okay? 당연하죠. So for the setup time, the input needs to be stabilized at this point. So this input T2, this T2 signal needs to be stabilized before setup time before the rising edge of the clock. So for this point, we need to consider the maximum delay. The maximum delay at this point. Then how can you calculate the maximum delay? So until the signal reaches this point, we need to consider the delay of Q1 from the this D flip-flop. Also, we need to consider the delay of combinational logic. Then what is the maximum delay for this point? The maximum delay is the maximum delay of this Q1 plus maximum delay of this combinational logic, right? So then max plus max becomes the maximum delay for this T2. So the maximum delay of Q1, that is the PCQ, the propagation delay of flip-flop. And the maximum delay of combination logic is the TPD, is a propagation delay. And then this delay needs to be less than the clock period, but before T0. Okay, so it is because this is the clock period Tc, but this signal needs to be stabilized before setup time. So we need to subtract T setup is a setup time from the clock period. You understand? So in order to meet the setup time constraint, which means we need to the timing property. The timing property of this circuit needs to meet this condition. Okay, do you understand? So we can get, so if we just rewrite this equation like the equation, then we can rewrite this equation like this. Okay, so it means that the clock period needs to be bigger than the TPCQ plus TPD plus T setup. Okay, so I said that the clock period needs to be bigger than this value, right? So which means the clock frequency, actually clock period, is determined by these timing values. Okay, so if we want increase the performance of this system, then which means that we need to reduce the clock period, right? Because the clock frequency is the inverse of the clock period. So which means in order to increase the performance, so we need to increase the clock frequency, which means we need to reduce the clock period. And how? So actually the PCQ and then T setup is the some fixed the fixed timing property. Okay, it's the some common timing property of three flip-flops. Okay, but this combinational logic, the combinational logic is the delay of combinational logic is determined by the combinational logic design, right? So which means if we use very complex design, very complex combinational logic design, then TPD can be large. Okay, because so you know the complex logic includes many logic gate, right? So in order to implement the very complex combinational logic, then this complex combinational logic will include many logic gates, right? So and the logic gates are actually circuit. So if there are many circuits, then delay is also increased, right? Because there are many circuits in the path. So actually, this TPD, and then usually, so TPD is proportional to the complexity of combinational logic. So it means in order to make the performance of the system high, so which means that you want to reduce the clock period, you want to increase the clock frequency, then actually this combination logic needs to be fast. Okay, and then the clock period. Actually, the clock period of this system is determined by TPCQ and plus TPD and then plus T7. Okay, so then actually we cannot change this part because this is the property of the flip-flop. So actually, the TPD is determined by the complexity of combinational logic. So which means actually we try to reduce this part when we design the system. Okay, so when we design a high performance digital system, then we need to reduce this part, TPD of the combinational logic. Okay, another constraint is the hold time constraint. So what is the hold time constraint? The signal needs to be maintained. So PPCQ is the propagation delay of this D flip-flop. Okay, so so we learned about the output timing. So D flip-flop has the output port, which means that, or actually this output port also exhibit delay from the rising edge of clock, because this is also circuit. So TPCQ is the propagation delay, which means the maximum delay of is port Q, and then TCCQ is the contamination delay of this port. Okay, so it's but TPD, this TPD is the propagation delay of combination analysis. Okay, you understand? Okay, good. Okay, then we need to also consider the hold time constraint. So what is the hold time constraint? The input of D flip-flop needs to be stable during the hold time from the rising edge of clock. Okay, so this is the rising edge, and then during this T hold, then the input needs to be stable. This is the hold time constraint. Then how can you analyze? How can you analyze the hold time constraint in this circuit? So you need to also focus on the D2. Okay, D2. Then so how can I explain? So you need to be keep stable during some time. but you can be changed, so you can be changed. Okay, then is this explain the minimum delay or maximum delay? So you need to be stable during some time, right? Then is this explain minimum delay or maximum delay? It's minimum delay, right? So during some time, okay, during some time, so from this time to this time, you need to be stable, which means that the signal is not changing. So which means actually this explains minimum delay. So which means that from this time, signal changes at this point. Okay, because this is the minimum delay. Okay, minimum delay. So if the minimum delay is less than this hold time, so which means that the signal is changing. Signal can be changed, right? Because the minimum delay and maximum delay explains some possible delay. Okay. So actually for this T2, this T2 needs to be stable during the hold time. So which means, the signal also starts from this Q1, okay? And then also you can find the combinational logic. And then, so T2 is determined by output of this combination logic. And then T2 needs to be stable. So which means we need to consider the minimum delay. So what is the minimum delay of Q1? The minimum delay is the TCCQ. And then what is the minimum delay of combinational logic? Minimum delay is the TCD, is a contamination delay. And then, so this delay needs to be larger than the T hold. Do you understand? So I said that during a certain time, then you need to be stable. So which means the signal cannot be changed. So it explains the minimum delay for this point, because so if the minimum delay is less than this full, then which means that it can be possible. It is possible that the signal values can be changed. Okay, so when we consider the hold type constraint of this D flip-flop, then TCCQ, so it's the minimum delay of Q1, and then TCD, so this is the minimum delay of this combination logic. The sum of TCCQ and then TCD needs to be larger than the T hold. Okay, so this is the hold time constraint. So actually, the TCCQ is some unique feature of the D flip-flop, so we cannot change. But TCD is also determined by combinational logic, the complexity of combinational logic. So, but it means that if the combination logic is not complex, so very simple, then TCD can be very, very small. But in this case, it can be a problem. Okay, so it is because the contamination. So if we just rewrite this equation, then it means that TCD, the contamination delay of this combination logic, needs to be larger than the T hold minus TCCQ. Okay. So, which means if the delay is very short, then it can be also problem in this case. So actually the setup time constraint in, so if you see the equation of the setup time constraint, you can find that clock period. So actually the setup time constraint determines the clock period of the system. Okay. So but hold time constraint, in order to analyze the hold time constraint in the circuit, then we need to actually calculate the minimum delay for this T2, this point. But actually, so if you see that this hold time constraint, then you cannot find any clock period actually. But hold time constraint just explains the minimum delay of this combinational logic. And then if this minimum delay is too short, too low, we also need to increase the delay of this combinational logic, okay, in order to meet the hold time constraint. Okay. So it's also important. If the hold time constraints are violated, then the system can work incorrectly. Okay, so we also meet the hold time constraint, but so hold time, in order to meet the hold time constraint, then we need to increase the delay of combinational logic. Okay, so I will show the example. Okay, so this is the example. So these constraints are very important, as I mentioned. Okay. So this is the example. So you can find the many D flip-flops, and then also here and here. And then also you can find the another D flip-flops here. So this is the some input point. So these D flip-flops, D flip-flops A, B, C, D, generate the input of this combinational logic, right? So this is the combinational logic, right? And then these D flip-flops X and Y receive the output from combinational logic. Okay. And then this is the timing characteristics of flip-flop. So TCCQ is the contamination delay of the Q, the output. So 30 picosecond, and TPCQ is the 50 picosecond. So this is the propagation delay of output Q. Then 0 times 60, the hold times 7. And then this is logic delay per gate. Okay, you can find some gates here. Propagation delay is 35, and then contamination delay is 25. So firstly, we need to analyze the setup time constraint. Okay, so and then in order to analyze the setup time constraint, so we need to consider the maximum delay, right? So you need to understand that for analyzing setup time constraint, we need to consider the maximum delay of this circuit. So what is the maximum delay? So what is the critical path for this circuit? So okay, so actually, so you know, this path includes the 3 logic gates. So which means this path determines the maximum delay, of this circuit, right? Then we can calculate the maximum delay. So what is the maximum delay? So maximum delay is so this is the T PCQ, right? This is the maximum delay of D flip-flop, and then plus TPD of this one, the gate 1, plus gate 2, TPD of gate 2, and then also gate 3, plus TPD of gate 3. So this is the maximum delay from the output of flip-flop to the input of flip-flop. Well, we can calculate. So this is goes so. Then what is the maximum delay? Maximum delay is 35 multiplied by 3, and then it's a 25. So what is the no TCD, no TCD. So TPD, the TPD1 plus TPD2 plus TPD3 is the 35 multiplied by 3, so it's the 105 picosecond. And then what is the TPCQ? TPCQ is the 50 picosecond. So what is the maximum delay? Maximum delay is the 50 picosecond plus, so this one. And then 105 picosecond. So this is the maximum delay at this point. So this is the 150 picosecond, but this plus T setup. Okay, this plus T setup needs to be less than the clock period, right? So we need to consider the setup time because the signal at this point needs to be stabilized. Setup time before the rising edge of clock, right? So maximum delay max delay plus setup time needs to be less than the TC. Okay, so maximum delay is the 155 plus setup time is 60. So this is the TC. Okay. So TC needs to be the clock period for this circuit. Clock period needs to be bigger than the 215 picosecond. So what is the maximum frequency? Maximum frequency is, so this is the minimum clock period, right? So the maximum frequency is, so it's the inverse of minimum clock period. So it's the 4.65 gigahertz. So by analyzing setup time constraint of the circuit, then we can calculate the minimum clock period. Okay, so which means we can calculate the maximum clock frequency. You understand? Okay, so this and then so this is one, and then let's analyze the hold time constraint. So I mentioned that in order to analyze the hold time constraint, we need to consider the minimum delay. So what is the minimum delay? What is the path for minimum delay? So this is the minimum delay path because only one gate. There is only one gate in the path, right? Then you can calculate the minimum delay. So minimum delay for this D is the TCCQ, and then minimum delay of this gate is the TCD. Okay, so this is larger than the hold time. This is the hold time constraint, right? So we calculate the minimum delay for this point, the input of D flip-flop, right? And then this minimum delay needs to be larger than the hold time. And let's check. TCCQ is the 30 picosecond, and then TCD is a 25 second. And then what is the hold time? Hold time is 70 picosecond. So this is 55. So actually less than the 70 picosecond. So what does that mean? This circuit violate hold time constraint, right? So it violates. So it is unstable system. This system is unstable because it violates hold time constraint. Then how can you fix this circuit? So it means how can we increase the minimum delay of this circuit? The problem is that minimum delay is too low, too small. Okay, the minimum delay is too small, so it violates hold time constraint. So system is unstable. So how can you solve this problem? We can increase. Then how? We can increase the delay. And how? We can add gate. So gate, if there are many gates in the past, then the delay will be increased. And how? We can add inverters, two inverters, right? So actually four, right? So if we just add the inverter gate in the past, then actually the value is the same at this point, but delay is increased, right? Because there are more gates. So if the hold time constraint is detected, then actually we can add inverters. Like we can add actually buffer. So this is the buffer, and then this is the inverter. But actually, buffer is the back-to-back inverters, right? Because the inverter is the same. The signal is the same. Signal value is the same. So actually, we can add buffer. So which means two inverters. So like this. So you can find the buffer symbol here, but actually, this buffer is the yes, two inverters. Okay, so by adding an inverter, so which means buffers, so we can solve hold time constraint issues. Okay, so it is interesting, right? So we need to add some logic. We need to add some circuits to solve hold time constraint. So it means that actually we need to invest. So we need to include more gates, which means the cost can be increased. But actually, in order to meet the hold time constraint, then we also need to increase the number of gates. So which means that the cost can be increased. But in order to make the stable system, we need to increase the cost. Okay. So actually, you can think that, it's so, how can we analyze the timing of this circuit? But unfortunately, So the timing. So after the circuits are synthesized, the timing of all points are analyzed by CAD tool. Okay, so and then so CAD tool calculate the maximum delay, and then also then CAD tool reports the available clock frequency. Okay, so and then so CAD tool analyze the maximum delay. Also, the CAD tool analyze the minimum delays between the flip-flop, and then if the minimum delays violate hold time constraint, then the CAD tool add the buffers. Okay, so it can be done automatically by CAD tools, fortunately. But you need to understand how the setup time constraint and hold time constraint is analyzed. It's very important. Also, so and then usually the setup time constraint decides the performance of system. So we can focus. So usually we focus on setup time constraint. So in order to increase the performance. Okay. Okay. So and then actually, so I hope you can understand this timing constraint and timing characteristics of circuit. So because this is some real property. So as I mentioned, this is not a simulation. This is the real implementation of circuit. So which means actually when we implement the real physical system, then this timing constraint needs to be considered. Okay, so I think we don't have enough time for the class Q. So I will explain about the class Q in the next class. Any questions? Okay, and then I'll try to understand this part. It's a very good thing. 감사합니다.